Now let's consider an example where we have two processes on our chemical processing site, process A and process B. And process A is being designed with a minimum approach temperature of delta T min 30 degrees centigrade, and process B is being designed with a minimum approach temperature of 10 degrees centigrade. And we have been provided the problem table information and the associated grand composite curves. We also have two steam mains available. So we have one steam that is at 225 degrees centigrade, and the other steam is at saturated temperature of 125 degrees centigrade. We have cooling water available at 30 degrees centigrade with target temperature of cooling water to be 35 degrees centigrade. Okay, and then we have the boiler steam is available at a saturated temperature of 350 degrees centigrade. This represents a high pressure for utility boiler steam, probably higher than most of the utility boilers produce their steam at. However, this is purely for illustrative purposes. Here we have the problem table cascade information of process A, and this shows a pinch temperature of 141 degrees centigrade, and then we have our QH min and QC min of the process, and the grand composite curve for process A is shown here. So above the pinch region, we essentially have our cold streams that need heat in the form of steam to provide external heating requirement. And then below the pinch, we have our hot streams, and that can be used to generate steam if we want so. Okay. And then we have our process B. Again, we have our pinch temperature, and then we have our QH min and QC min. And remember that this process is being designed at a delta T min value of 10 degrees centigrade. We have our associated grand composite curve for process B, showing us the heating requirement. Okay, and then below the pinch, we have large amount of heat available that can be used for steam generation below the pinch, and as you can see that the temperature is much higher here compared to the process A. So now let's move on to see how we would solve this in terms of producing our site profiles, adding our steam mains to produce our total site profiles, and therefore target for steam generation and steam use from these two processes, and then see if we have heat recovery through our steam mains or not. Here we have the grand composite curve for process A, and in this case we have added the coordinates values where there is a change in slope in the grand composite curve, as you can see here. And the coordinates are the temperature values and the heat duties. And we have done that both for above the pinch and below the pinch. And we are going to make the assumption that we are not going to extract the pocket here, and the pocket is self-contained as we saw for our usual pinch analysis as well. Now we are going to look at which streams we can extract in terms of the cold streams and the hot streams. Cold streams will need steam heating from our utility system, and our hot streams below the pinch can be used to generate steam. So we have cold streams going from 145.1 degree to 160, and then 160 degree to 165 degree, and then finally we have a third cold stream going from 165 to 275 degrees centigrade. Below the process pinch, we have our hot streams going from 145.1 to 120 degrees centigrade. Then we have our other hot stream going from 90 to 80 degrees centigrade. So we can now place those streams in a table, and this shows our effective temperature that we have to apply for the process delta T min is 30 degrees centigrade on the grad composite curve. So the temperature of the hot stream and the cold stream have already been shifted by 15 degrees centigrade, that is half of the delta T min. And to produce the total site profile, we have to shift the temperature by a further 15 degrees centigrade. So for the cold stream, we have to upgrade by half a delta T min, and for the hot streams, we have to downgrade by half a delta T min. So we have our first stream, that is our cold stream. So we have a supply temperature of 165 degrees centigrade from grand composite curve and a target temperature of 275. And if we shift it by half a delta T min, so this temperature will become 180 and the target temperature will be 290. And by doing that, we have shifted the stream by a whole delta T min compared to their original temperature. And we can read the delta H, the heat duty of this stream from the grand composite curve. And then if we use delta H is equal to Cp delta T, we can calculate the value of Cp, that is 25 kilowatt per degree centigrade. So using the same method, we can extract the data for the next two cold streams, that is going from 160 to 165. We will shift it by half a delta T min and then calculate its heat duty and Cp. And similarly for the third cold stream, going from 145.1 degrees centigrade to 160 degrees centigrade, and then we will shift it and calculate its Cp value. We also have two hot streams that need to be extracted from the grand composite curve. So we have a supply temperature of 145.1 degrees centigrade and the target temperature of 120 degrees centigrade, that is shifted by half a delta T min. And then we downgrade them by half a delta T min further. So it will be from 145.1, it will be 130.1, and then from 120 to 105 degrees centigrade. And we can read the delta H from the grand composite curve, and then we can calculate its Cp value. Okay, and similarly for the other stream, we have going from 90 degrees centigrade to 80 degrees centigrade, and again using the same method, we can calculate its heat duty and the Cp value. So we have three cold streams and two hot streams in this grand composite curve. So these streams, we have already extracted the data, and now we can use this table to produce our total site profile. We now move to process B, and again we put on the coordinates representing the change in slope on the grand composite curve. And again we recognize the existence of the pocket here, and we may have to interpolate in terms of the temperatures if the pocket doesn't happen to coincide with the change in the slope. In this particular case, we have two cold streams above the pinch. So we have that we need to actually heat from our utility. So we have a stream going from 255 to 260 degrees centigrade, and then a stream going from 260 degrees centigrade to 285 degrees centigrade. Below the pinch, we have far larger amount of heat that is available. So we have our hot stream that is going from 255 to 166.5 degrees centigrade, and then we have another hot stream that is going from 130 degrees centigrade to 105 degrees centigrade. Please note that the stream here going from 140 to 130 degrees centigrade is not extracted because there is no duty involved, and so we don't really need to extract this stream for our process. We can make a similar table for process B like we did in process A, with our supply and target temperatures from our grand composite curve, and then shift them by half a delta T min. And the delta T min for process B is 10 degrees centigrade, so half of delta T min is 5 degrees centigrade. And then we need to shift these supply and target temperatures by upward by half a delta T min. So that would be this stream going from 260 to 265 degrees centigrade, and in terms of target temperature going from 285 to 290 degrees centigrade. Again, we can read the value of delta H from the grand composite curve and calculates the CP of the stream. So here we have two cold streams, and then we have two hot streams. So for the cold streams, as you can see that we definitely need to provide them heating to reach their target temperature, while for the case of hot streams, we can use them for steam generation below the pinch. We can then go ahead and produce our composites of our source stream and our composites of sink streams. So first of all, composite of our source stream, and these streams we recognize as hot streams that have heat available for steam generation, and we produce our site source composites in the same way as we would produce a composite of our hot stream that we have seen in process integration unit. And we recognize our streams that have the heat available here. So we have these streams within these temperature intervals here, here, and here. And our total heat content for all these sources or hot streams is 2566 kilowatt. We can do the same thing with our site sink streams, and these are our cold streams that we have extracted from process A and process B. And again, we will show our cold streams in their respective temperature intervals, and the overall heat content of all these sink streams is 3948.5 kilowatt. So we can plot those site source and site sink profiles the same way as we plot hot and cold composite curves. Okay, and here we see our source profile representing the hot streams that we extracted from our grand composite curve that could go on to generate steam. And here we can see our sink profile representing our cold streams that we have extracted from grand composite curve of process A and process B, representing the heat needed to be provided by our steam use from our utility system. We can now use our site profiles to target for steam generation and steam use, and we call these site profiles with steam generation and steam use as our total site profiles. And we can see the steam generation of steam here at our saturated temperature of 225 degrees centigrade. We show the utility stream at their actual temperature, at the real temperature, and consequently where they touch the actual profile, we have a delta T min of the original value for the process. As we have shifted our hot stream down by a whole delta T min, there is a whole delta T min in between our real temperature of the steam generation and the actual process that are generating the steam. Again, we are showing the amount of steam that is generated at our low saturation temperature of 125 degrees centigrade. On the sink side, we have we required this amount of steam for our cold streams to be provide the heat. And again, where this curve touches the composite curve, there is a whole delta T min difference between the real temperature of the steam and the process temperature of these cold streams that require the heat which has been shifted by a whole delta T min value. The higher temperature requirement of our process A and B is met by the use of steam from our utility system boiler that is at 350 degrees centigrade. We can then start to overlap the total site profiles in order to calculate and target for the amount of heat recovery in our utility system. We have pushed our sink profile towards our source profile, and we get a certain amount of overlap between our profiles, which has consequently reduced the amount of this VHV steam that we are getting from the boiler. We can now extract our relevant targeting information from our total site profiles and our total site composites. From our total site profiles, before we consider heat recovery through the steam mains, we have to provide 3948 kilowatts of very high pressure level from our utility boilers. When we push our profiles together in order to achieve some heat recovery through the steam mains, as shown by our total site composites, this very high pressure steam from our utility boilers reduces to 3448 kilowatt. That is a saving of 500 kilowatts of the very high pressure steam. We can also show our HP generation and LP generation and use. So for our HP generation, we are producing 1502 26 kilowatt, and we have an HP use of 500 kilowatts. So we are generating far more HP steam than we have to use. So consequently, that extra generation more than meets our HP steam use, and we can use that 500 kilowatt to reduce our very high pressure steam use from our boilers. Our LP generation is 1321 kilowatt, but we are not using any of the that heat from the generation of steam, so it would need to be passed to the cooling water, and our cooling water use is 745 kilowatt. So in summary, we can use the individual utility heating and cooling demands of our process, and then we can produce site composite curves from that data. And then by using the site composite curves, we can set the targets for steam load and also the targets for heat recovery through steam system or the steam from boiler and heat ejection. And I hope this work example would help you understand the concept of site analysis and how we can use it. So that is the end of this part. Thank you for your time.